All right, welcome to Physics Essentials video 3.5. We're going to learn about what's called conservation of energy. We're just going to kind of get into the basics of it here. By the end of this video, here are your objectives. You should be able to understand and find an object's total energy. You should be able to state and explain the law of conservation of energy. And you should be able to apply the law of conservation of energy to various situations. And that will make more sense as we get a little bit further into the video here. All right, so here we go. Total energy is exactly what it sounds like. It's the total of all the different types of energy that an object has at a given moment. So to find the total energy of an object, you take the kinetic energy and the gravitational potential energy and the elastic potential energy and the electric potential energy and the chemical potential energy, and you add them all up. Add them all up, right? Okay? Now, for us, usually what happens in physics is, because of the types of motion we're studying, usually you're not going to need to worry about elastic potential energy, electric potential energy, or chemical potential energy. And so as a result, this is what is usually going to be our total energy. You're just going to add up the kinetic energy and the gravitational potential energy. Okay? Probably worth reviewing for you if you don't remember this. In the last video, we learned that the kinetic energy depends on the velocity of the object and the mass, and the gravitational potential energy depends on the height of the object and the mass. Okay, so your total energy is usually going to depend on those two things. Okay, so there we go. So here's an example. Suppose that Roy fires a water balloon at Sally. All right, and when the water balloon is at the very top of its path, because it's up some height, it's going to have some gravitational potential energy, right? All right, so maybe it's got 20 joules of gravitational potential energy. Don't worry about where I got the 20 joules. It's just a made-up number, but you'll need to understand that it's not zero because it's up some height. Also, the water balloon is moving. And since kinetic energy depends on velocity, there's going to be some kinetic energy too. So maybe you take a photograph of the water balloon when it's at the top of its path. Because it's high up, it's got 20 joules of GPE. Because it's moving, it's got 30 joules of KE. Add them up and you get a total energy of 50 joules. That's all there is to it. You just add them up to get your total energy. All right, and then down here at the bottom, there's a little side note. It says, note, technically the water balloon also has elastic potential energy since it's stretched out, right? The balloon is stretchy and is stretched out. But we're not going to worry about elastic potential energy. We are not going to worry about elastic potential energy, chemical potential energy, or electric potential energy when we're solving problems with numbers. All right, so just be aware of that as a side note. Okay, so here's the law of conservation of energy. All right, law of conservation of energy says this. Everything above this line is the law of conservation of energy. It says that energy cannot be created or destroyed. Energy can only be converted from one form to another or passed from one object to another. All right? And so the result of that, what that means to us, and this is super important, what it means to us is that as long as energy is not passed from one object to another, an object's total energy is always going to remain constant. Okay? So in other words, you might gain GPE and lose KE or vice versa, but the total amount is going to stay the same. All right, so let's do a quick kind of numeric example to help you think about this. All right, so the first example I want to talk about is dropping a ball off of a roof. All right, so the idea is we've got this ball that's up some height, right? Because it's up some height, it's going to have some gravitational potential energy, right? So again, there's a way to calculate it. We're not going to worry about how to calculate it, but just know that it's going to have some gravitational potential energy. So that we can do our calculations, I'm going to make up a number. So maybe it's got, whatever, 80 joules of gravitational potential energy, okay? Because it's way up high at the top of the building, right? Now, because when you drop something, remember your velocity starts at 0, that means that the kinetic energy of the ball at the top of the path is 0 joules, right? Because it's not moving, right? Okay, so what we can do is we can figure out how much total energy the ball began with. Before our dude here, Roy, lets go of the ball, the total energy is 80 joules of GPE plus 0 joules of Ke gives you a total of 80 joules, right? Okay, so then the ball's going to fall down, right? So let's suppose we took a couple snapshots of the ball on the way down, okay? So suppose we took a snapshot of the ball when it was, say, I don't know, here, and another snapshot of the ball when it was here. Oh, I wanted to do this in different colors, sorry. Another snapshot of the ball when it was there, and another snapshot of the ball when it was right here in the process of hitting the ground, okay? So the idea is, as the ball goes down, the height gets smaller and smaller, right? So, for example, here at this green spot, the height is going to be some smaller number. So that means you're going to have less GPE. All right, so maybe the GPE here is, and again, I'm going to make up a number. The only important thing is that it needs to be smaller than 80 joules, right? Okay, again, there's a way we could mathematically calculate it. All right, let's suppose that the GPE at this point is 50 joules. Okay? Then when the ball gets to down here, the blue dot, you're going to have even less height, which means even less GPE. So maybe now the GPE is, I don't know, let's say 20 joules. And again, I'm just making up numbers here. All right? And then finally, when you get down to the bottom down here, the ball is, for all intents and purposes, on the ground. So now the height is 0, which means that the GPE is going to be 0, right? Remember, any object that has no height also has no gravitational potential energy. All right? So, remember, you guys, what we learned in the previous slide was this. An object's total energy will always remain constant. Okay? As long as the energy is not passed from one object to another. So the ball doesn't have any way to transfer energy, to anything else. It's not touching anything. So our total energy has to be the same. So what that means is, up here at the top, we found out that our total energy was 80 joules, right? When the ball was right here, right? So what that means is, at all of these other points, the total energy also has to be 80 joules. So over here, our total energy has to be 80 joules. Okay, when you get down to the blue point, the total energy has to be 80 joules. And right before the ball hits the ground, down here, the total energy has got to be 80 joules, right? That's what conservation of energy tells us, is that the total energy stays constant. All right, so let's go back up to this green point for a minute. Look, at the green point, our GPE is only 50 joules. We've got 50 joules of gravitational potential energy, but somehow we've got a total of 80 joules. So we're missing 30 joules somewhere. Well, where did that 30 joules go? Well, let's think. The ball is now moving downwards, right? And as a result, it's going to have some kinetic energy. And so to figure out how much kinetic energy it has, we got to figure out, what do we have to do to get us up to 80? We've got 50. We need 80. So there must be 30 joules of kinetic energy, right? Which makes sense, because it's moving now. It's going to have some kinetic energy, right? So now when you get down to the blue part, it's going to be going even faster, right? When you get right here, it's going even faster. And what that means is there's going to be even more kinetic energy. So think about how much. Well, we need to get up to 80, and we've only got 20. So that means the kinetic energy here must be 60 joules, right? It's the only way it could add up. All right? And then the ball is moving its fastest right before it hits the ground. And since the GPE is 0, that means that the kinetic energy has to be 80 joules to keep the total 80, right? All right, so what's happening here, you guys, if you did not follow this, is the ball started out with 80 joules of gravitational potential energy, right? As it falls, it loses gravitational potential energy because the height decreases, but it gains kinetic energy because the velocity increases. Okay? And so by the time it hits the ground, it's lost all the GPE, but gained that much kinetic energy. So the energy has just transferred forms. It's changed from GPE into KE. Okay? So these couple sentences here kind of summarize what we just talked about. The idea is as the ball falls, the height decreases, and as a result, the GPE decreases, right? But remember, energy can't be destroyed. So as it loses the GPE, it's also going to gain kinetic energy because the velocity is increasing. Okay? So let's do another example. This one we're going to do without any numbers. So let me see here. So here we've got our skate park, all right? And so up here we've got a dude here, skateboarder guy, who right now has, oh shoot. We've got a dude who's got a whole bunch of potential energy, right? Look, right here, it shows you his potential energy. It's this big number, right? But he's not moving right now, so his kinetic energy is 0, right? Okay. Don't worry about this thermal energy over here. Just ignore this. Okay. So right now, his total energy is just no kinetic energy plus a lot of potential energy gives him this amount of total energy, right? All right. So what I'm going to do is I'm going to let him roll down the hill. All right. So boom. And boom. So look what happens as he goes down the hill. As he goes down the hill, watch what's happening. As he goes down the hill, this potential energy here is going to decrease, but the kinetic energy increases, right? So it's going to be, I wish I had 2 pointers here, but as he goes down the hill, the potential energy is going to decrease, and the kinetic energy is going to increase, but the total is always going to stay the same. All right? Then when he goes up the hill, it's going to be the other way around. As he goes up the hill, the potential energy will increase, and the kinetic energy will decrease. All right? So, watch. All right? His potential energy is at its highest. Now it's decreasing. Kinetic energy is highest. Potential energy is at its highest, and it just goes back and forth, right? Okay, and you can see up at the top up here, there's a little speedometer, right, that helps you see it, right? His speed is increasing, decreasing, increasing, decreasing. And then his height decreases, increases. His height decreases, and then increases, right? Okay, and so that's all that's happening, is as he goes down the hill, he loses height, he loses potential energy, but he gains velocity and gains kinetic energy. And then going up the hill, it's the opposite. Okay, but the total stays the same. Cool. I think that's it for that slide. So, pause. No. Pause. All right, here's our last example. This is kind of the classic example you'll see in any physics class in the universe, which is the roller coaster example, all right? And so the idea is our dude up here is way up at the top of the hill, so he's got a lot of height. He's got a big height, which means he's going to have a big amount of GPE, right? So let's make up a number. Maybe it's, whatever, I don't know, let's say 800 joules, okay? Now, when he goes over to the top of the hill, he's moving, right? So he's going to have some velocity, but not very much, right? So he's got a small velocity. He is moving, though. So let's say he's got a little bit of kinetic energy. I'm going to make up a number again. Maybe it's 200 joules of kinetic energy. So what that means is when he goes over to the top of that hill, his total energy is 800 plus 200, or 1,000 joules, right? Okay. Now, as he goes down the hill, like this, he's going to lose GPE, but gain KE, right? Because as he goes down the hill, he's going to lose height and gain velocity. So when he gets down here to the bottom, now his GPE is going to be some smaller number, right? Because he's not as high up. So maybe now down at the bottom of the hill, I guess it depends on where the ground is. Let's draw the ground in. Okay, since he's not quite on the ground, he's still going to have a little bit of GPE. So again, I'm going to make up a number, but maybe it's 100 joules. Remember, the whole premise is the total needs to stay the same. So the total energy is still 1,000 joules, which means that at that point, the kinetic energy has got to be 900 joules, right? Okay. Then over here, when he gets to the top of this hill, whoa, I don't know what happened to him there. He's higher up than he was at the bottom, but not as high as he was at the top. So maybe now his GPE is I don't know, 500 joules. His total still needs to be 1,000 joules, which means his kinetic energy has got to be, well, how much more do we need? We've got 500, we need 1,000, so we need another 500 joules, right? All right, so the idea is the entire time you're on this roller coaster, all you're doing is you're converting energy from one form to another, okay? And also notice that, suppose I drew him over here again. Okay, at these 2 points, the height is about the same thing, right? So at both of those points, you'd have the same GPE and the same KE. Okay. I think that's it. This is going to take you guys a little bit of practice, but that is the major idea there. If I was to summarize everything that we've just learned here, I would summarize it by referring you back to that slide right there. Okay, so read it, think about it, and I'll see you in class.